Hey there, welcome everyone, thanks for being here. So glad you can join us. Get yourself ready with a notebook, a pencil, or pen, whatever you choose to write with is fine. This is math from the void, math coming at you out of nowhere. And today we have a problem from the 1992 Calc BC exam. So students in AB Calculus, this one is not for you. This is for students in BC who have studied series and determining whether or not series are convergent or divergent. Definitely a BC topic, so do not feel obliged if you're an AB student, especially at this time when you're studying for your own exam. Can't really spare any time on topics that you're not even going to be tested on, right? You can learn these BC topics next year. So give this a look, and also make sure that you give yourself about 12, maybe 15 minutes if you really need it. We're not going to be using Desmos today, as this problem doesn't require any calculators at all. Just conceptual understanding. Some tests for convergence and divergence, a little integration, and let's get started. So if we consider the series, I had to include the sigma because for some reason the sigma didn't come out very well. The series from 2 to infinity of 1 over n to the p times ln n, also in the denominator. The first task is to show that the series converges for p greater than 1. Well, we're going to do that by a simple direct comparison. Because if you remember, this series here oops, 1 over n to the p. This is convergent. This is called a p-series. And this is convergent for any value p greater than 1. And that's the condition that we have. And we're going to notice something. This series, which includes the n equals 1 term, I did intentionally put that there, even though the question specifies from n equals 2. This n equals 1 term is going to cause whatever this sum is to be greater than whatever this sum is, because we're basically just excluding 1 over 1. So it's smaller by 1, by the first term, which is valued at 1. But this is also greater than something whenever we're multiplying the denominator, if we're making it larger, that is. So we have to mention that ln of n is always greater than 0 as long as n is greater than 2. Well, technically as long as n is greater than 1. And since n starts at 2, we know that it's greater than 0. Therefore, n to the p times ln of n is greater than n to the p for n equals 1. N greater than 1, sorry. Therefore, this series is also, let's do one more logical step. Therefore, 1 over n to the p, ln of n, must be less than 1 over n to the p. Okay, so we've established that all of the terms are now smaller. And then we can use this to say that means the sum from 2 to infinity of 1 over n to the p, ln of n, is greater than, not ln of n yet, greater than this series that we're really interested in. 1 over n to the p, ln of n, and of course this is with p greater than 1. So because a convergent series, this one, is greater than this convergent series, which is greater than this convergent series, that's the same one, which is greater than this convergent series, that means this is also convergent. So we can say convergent by direct comparison. Sometimes I put DCT, but it's fine. I'll just write it out, direct comparison. And it doesn't ask us to find what it converges to, it just asks us to prove that it does converge, to show that it does converge, rather. Okay, not so bad. Not really an answer to box, it's just sort of all of the logic along the way. So we need to indicate that the terms are smaller in the denominator, and we also need to indicate that that is because of this fact about ln of n, which it's only positive when n is greater than 1. Okay, part B. Determine whether the series converges or diverges for p equals 1. This one is pretty interesting because we know that, the integral from 1 to infinity of 1 over p, this diverges. And we know that this sum, 1 over n to the, wow, why did I do that? I meant 1 over n to the 1, p is 1. 1 over n times ln of n, we know that this is definitely smaller. But that doesn't help us. If we say that it's smaller than a divergent series, we don't know if this is also divergent. So this is going to be 1 over n to the 1. So that direct comparison would be inconclusive. We need a different way to determine whether or not this series converges or diverges, since this isn't a sort of clear p-series that is convergent. It's not clear that this is convergent or not. So we're going to have to try the integral test for this. And in order to try the integral test, what does the integral test say? Let's try to type here. Can we not type? Okay, we can't type apparently. So the requirements for the integral test are that we have to check if it's always positive, that it's decreasing, so that's going to involve taking a derivative and making sure that it's always negative. And we also need the limit of the sequence to go to 0. So we need to know that it is collapsing. And if we can verify those three things, then the integral test says we can check for convergence and divergence. It doesn't give us the convergent sum. It just tells us that we could use an integral to validate whether or not it converges or diverges. And that's all it's asking for, to determine whether it converges or diverges. So our analysis is really going to come down to checking these things and also taking the integral once we've checked those three things. So we know that n ln of n is always positive because we know that n is greater than 1 in this case, for n greater than 1. So therefore 1 over n ln of n is also positive. So that's a check. For decreasing, we need to check to see the derivative. Now there are a couple of ways to do this which sort of avoid using a derivative. We can use reasoning. We can say n is increasing. We can say ln of n is always increasing. Therefore, n times ln of n is always increasing. And therefore 1 over that, since 1 is staying the same, but this thing on the bottom is getting bigger, this is always decreasing. So that technically checks it. If you want to do a derivative and just show that it's always negative, that's fine too. You can, I'm not going to stop you. And then we need to check that the sequence goes to 0. Well, of course, that's pretty clear, right? Because we just mentioned that the denominator is always getting bigger and the numerator is just 1. So of course the limit as this goes to infinity is 0. So for sure it qualifies for the integral test, which means we can use the integral not to find whether we get a value. We will get a value, but that's not really the point of it. The point of it is to check if we get a value at all, if it's convergent. And if it is, then the series will also be convergent. This sort of says that our integral, which doesn't exactly give us the sum, is sort of right on pace with the series, and therefore it is conclusive whether or not it's convergent or divergent, but it's not running at the exact same speed and racking up the exact same miles, you might say. So the overall sum is not the exact same distance traveled. That's one way to think about it. Okay, let's find the integral here. We need to find the integral from 2 to infinity of 1 over n ln of n. This is just a simple, you could do a u sub if you wanted to. I guess what I'll say is we're checking 1 over x ln of x. Maybe it's just me stuck in my ways using x's. Of course, we can't figure out exactly what that is because we're not allowed to integrate to infinity, but we can send t to infinity, and then we can take an integral from 2 to t of 1 over x ln of x dx. And the antiderivative here is simply ln of x. If you do like a mini u sub, this is your u, 1 over x dx, that's your du. Pretty straightforward. So this is just 1 over u, and then you integrate that, you get ln of u, which is ln of x. And we're taking the limit as t goes to infinity. That's 2, that's t. So here we can break this up. We can say ln of t minus ln of 2. And we want to send t to infinity. We want to, that'd be nice. But of course, this is going to diverge because this is going to go off to infinity. Ln of t goes to infinity. That's the inside of another ln, so ln of that also goes to infinity. So we can say for sure that this diverges. Therefore, the series diverges. And of course, we can't find the sum of the series. We don't know what it adds up to, but we know that it diverges for sure. Okay, great. Part C says show that the series diverges from 0 to 1 for p. These are values for p, by the way. Interesting. Well, if p is from 0 to 1, what does that change exactly? Does it make the numbers smaller in the series or in the sequence? Let's think about that. Like if we have 1 over 1, oh, whoops, sorry, 1 over 2, that's where you start. ln of 2 plus 1 over 3, ln of 3, plus 1 over 4, ln of 4, right? That's the series that we're given for p equals 1. Now, if p is less than 1, we would have some kind of number that's going to get smaller. We have some kind of radical. So this would be something like 1 over square root 2, for example, ln of 2. Or maybe cube root, or maybe some other root. But it's a root that's smaller than 1, basically. 1 over square root of ln of 3. So you'll notice that those terms, they're smaller in the bottom, which means overall the terms are bigger. And we can kind of directly compare that by taking, by comparing, literally, the terms in the sequence. So if we take an as 1 over n ln of n, and if we take bn as 1 over n to the p, let's pretend we don't know what p is equal to for the moment. If we take a ratio of those terms, then we end up getting 1 over n ln n, 1 over n to the p ln of n. And this will kind of nicely just flip, multiply, cancel, and we end up with n to the p minus 1. That's just it. Now, since p is between 0 and 1, right? Since that's the case, that means that we could just say n to the k, where k is less than 0, and therefore this is equivalent to like 1 over n to the k, right? Again, where k is some negative number. Oh, sorry. 1 over n to the negative k. Now, if we take a limit of that, this is called the limit comparison test. If we take the limit as n goes to infinity of an over bn, that's the same as the limit as n goes to infinity of 1 over, let's just call it 1 over n to the k, where k is less than 0. Oh, actually, we can call it now 1 over n to the s, I don't know, where s is greater than 0, because we flipped it onto the bottom, right? K was negative, but if we flip it on the bottom, now it's positive. And this, of course, is going to be 0. Since that limit exists, it's a convergent number, we know that they either both converge together or they both diverge together. So Bn from 2 to infinity converges. I'm going to put converges with, sorry, diverges. Oops. Diverges. The limit converges in their comparison, which again, kind of like the integral test, means they're sort of paced the same. If one of them's going off to infinity, they're both going off to infinity. If one of them's going to be slowing down, the other one's going to be slowing down. Maybe not at the exact same moments, but they're at the same pace. Diverges with sum of an. And we can say by limit comparison test, not the direct comparison. You probably could do direct comparison as well. I don't think you had to do limit comparison. You probably just could have compared each of the terms like I was sort of getting at over here. And you say that since their difference is positive because the top is always, the bottom one, this one is always bigger than the top. We can just say that all the bn terms are greater than all the an terms. So then that means the sum, yeah, that would have actually been way easier. So the sum is greater than this sum, but we knew that this sum was divergent. So there are lots of different ways to do some of these series analysis. Whichever way is more comfortable for you is fine. I'm here to sort of throw them all out there. Also to work under a bit of a time crunch, but with series, I think there's a little bit more illumination that I can do. I can light up some more of these crevices in your mental pathways when you're trying to solve these problems, just to give you more tools to work with and not make you feel like there's only one way to do everything all the time. Okay, anyways, that's enough blab out of me on this interesting series problem. We had to do a few tests. Make sure you're familiar with some of those tests for convergence and divergence. And I'll see you next time in the void.